In this video, I'm going to show the image of why you need a current source. From the why differential signaling video, we've known the differential signals are preferable to reduce the design challenges of crosstalk, supply switching noise, reference, or common mode noise, etc. Then, let's apply the signaling to the amplifier building blocks. If we take the common source amplifier as an example, the left-hand side is single-ended, which is very sensitive to the supply noise from the VDD. First, if the VDD moves up, the VR1 will move up and vice versa. In addition, the single-ended common source amplifier will be sensitive to the input disturbance as well. So, second, if the input Vin1 moves up, the output VR1 will move down and vice versa. Obviously, we've known the output noise of the differential-ended amplifier could be much less sensitive to the supply noise and common mode noise or interference. How can we convert a single-ended common source amplifier to a differential amplifier? Bingo! It's straightforward to just combine both single-ended common source amplifier and take both input and output differentially on the right-hand side. For example, the input of the differential amplifier will be Vin1 minus Vin2, and we just take the output Vout from the VR1 minus VR2. Furthermore, the waveform of the Vin1 is the inverse of the Vin2. Similarly, VR1 will be the inverse of VR2 in polarity. Therefore, only the differential signals at the input Vin and the output Vout are applied in the series system. What happens if the VDD or input common mode voltage varies? First, if the VDD moves up by VA, both the VR1 and VR2 will move up by the same amount, Vx. But the Vout does not move at all, since Vout is VR1 minus VR2. Does that make sense to everyone? Second, if both input common mode noise of Vin1 and Vin2 move up by Vy together, both output VR1 and VR2 will move down by Vz together. Then the differential signal Vout does not change at all. Therefore, the differential amplifier seems to achieve what we want, which is less sensitive to the supply and common mode noise. But do you see other implications if the input common mode DC level move too much here? Think about the common mode voltage image for 5 seconds. Correct. The output DC bias is not well defined, no matter the left-hand side or right-hand side, since both topology would be the same from the DC operating point. The output DC level highly depends on the input DC level. If the input DC level is low, and then the output will have a high DC level with a small AC signal swing. On the other hand, if the input DC level is high, and then the output will have a low DC level with a big AC signal swing. Would this DC level dependency between the input and output cause any signal distortion issue? Think about your image for 5 seconds. Right. Under the limited supply level, the input DC level plus AC swing must be within a certain range to maintain a valid amplifier application. Let's look at the waveform image with the same input swing but different input DC level as a case study here. As you can see, on the left-hand side, the low input DC level case leads to the output DC voltage plus output AC swing still under the supply level. Then the output swing exactly twice the input swing in a valid amplifier operation. If the right-hand side input levels could be too high, and then the output DC level plus the output AC swing could be beyond the supply level, then the maximum output swing may be pinched or clipped. So, how can we make a well-defined common mode voltage to avoid the signal distortion? Correct. Current source or ideal current source. For example, if the ideal current source is added at the differential pair's common source in the right-hand side, the output common mode DC level would be well defined to be VDD minus half IS times RD. Then the output common mode DC level can be easily designed properly to avoid invalid operation, even with multiple cascaded amplifiers. Please be advised that the current source will mitigate the design change of any single entity amplifier as well. Now, we know why we need a current source, but how good is the current source we need? Any idea? Think about the accuracy images for 5 seconds. Bingo, accuracy. The output common mode DC level is well defined by the current level IS of the current source. Therefore, the current accuracy is very important. In other words, you may want to get the exact current level as what you want. Besides accuracy, what else do you need? Think about the headroom images for 5 seconds. Great. Last headroom limitation or last voltage drop at the current source is necessary, and ideally would be 0. As you can see, the input level must be larger than the differential pair threshold turn-on voltage plus the voltage drop. Therefore, if the voltage drop across the current source VD is larger, then the input swing of the Vin would be limited. The amplifier's goal is to boost the signal-to-noise ratio and then reduce the bit error rate. Therefore, increasing the signal swing is the goal, but adding the current source would decrease the signal swing if the voltage drop across the current source is too much. Why else you should pay attention to the current source impairments? Think about the noise images for 5 seconds. Correct. A thermal noise or flicker noise at the current source could be a concern if the noise level is not small enough. But you may be wondering that the noise of the current source would be a common mode noise and should not matter at the output of the differential amplifier. Think about the mismatch images for 5 seconds. Bingo! As we discussed in the wide DC offset cancellation video, there's a device geometry and property mismatch at the differential pair. In addition, the bias condition of both differential pair at the input gate and output drain are different. Therefore, the common mode to differential mode conversion will make the current source noise still show up at the differential output. Therefore, an ideal current source without noise, or to make the noise as little as possible to some degree, is still needed. Anything else? Think about your impedance image for 5 seconds. Right, ideally, to make the current source output impedance to infinity. Remember, the current source is to set the DC common mode of the output. So, the DC current should be as stable as possible without interfering the AC signal. If the current source impedance is close to infinity, the AC small signal current will not flow to the current source. Instead, the AC current will only flow through the differential pair M1 and M2, such that the output differential swing will only depend on the input voltage, Vin and the GM of the M1 and M2 times RD. On the other hand, if the current source impedance is low, then either the amplifier's output swing or gain would be degraded by the current source. Here are the summarized images of why you need a current source. Since the current source will set a DC voltage level properly for either a single-ended or differential amplifiers, it's a necessary bias block for all kinds of analog blocks in a series system. Even though the differential amplifier is preferable to a single-ended one, the current source still needs to be precise, with less voltage drop, noiseless, and infinite output impedance to reduce the impairments of the differential amplifier. Again, please be advised that the differential amplifier is just a case study of why you need the current source, since the Kermel logic CML amplifier is the most extensive used analog block. The 36 other circuitry would also require a current source for robust biasing, and the corresponding requirements would be almost the same as a better accuracy, a less headroom consumption, a low noise, and a higher output impedance if possible. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.